Factor analysis. And the idea with factor analysis, we've talked about repackaging the information. Factor analysis repackages information in correlation matrices or covariance matrices. Covariance matrix is just the standardized correlation matrix. Plus a little other stuff. So in factor analysis, what we're going to do is we're going to take the correlate. We've got all these variables. So we take we get all these 20 questions or those 12 questions about parenting. Take a scales about behavior or attitudes towards whatever. We look at the correlations, and it basically it's in essence, it's going to put together these sorts of linear combinations that we'll see. It's going to reorganize that information, those correlations. It's going to reorganize the information that's in the correlations into these new scales, these new boxes that are called factors or principal components, same thing, more or less. Kind of one of the rules we're going to see is the factors are going to be reorganized into these factors that typically are uncorrelated with each other, but they don't have to be. And we're going to talk about the amount of information that's captured by a factor is measured by what's called an eigenvalue. Each variable adds 1 to the total eigenvalues that we're going to see. And you can think of what eigenvalues are. We'll see this again in a minute. You can think of an eigenvalue is variance of a matrix. It's how much variability there is in a matrix, or a box of numbers, a set of numbers. So to take a step back, going back to our whole moving day example, we're going to take the correlation matrix tells us how the variables are correlated with each other. So we start off with our original boxes and see kind of, how are things in those boxes related to each other? And we start to notice, I've got shoes here and shoes there and shoes there. Or, look, I can. There's summer clothes, summer clothes, summer clothes. It looks at that information that's contained in those original boxes. And then we're going to come up with these new factors. Those are those new boxes. And it's going to put the information and the variables into each of those boxes, into each of those factors. And then we're going to be talking about the factors. How much, once we're done, we don't worry about the variables anymore because we kind of tore them apart to put them into these factors. How much stuff we're able to squeeze into a box, we measure by the eigenvalue. It's kind of like the weight of the box. When Chopin just went on her plane, after that we were up early that morning weighing her suitcases so that we didn't. Actually, there's the example. So we didn't have to pay the extra $50 fee for the going over the weights. The eigenvalue is the weight of the box. How much information's in there? So let's kind of go through an example. And if that seems kind of weird, kind of crazy, that's okay. Hopefully it'll start to gel as we go through this. You may see some of those connections. So let's say I'm doing a factor analysis, and we're going to keep it simple. I've got 4 questions. I've only got 4 questions. And I'm going to look at how much information's there. Can I reorganize this information into fewer than 4 variables? Maybe things are really, let's take a look. One thing that we see, so we're going to try to repackage that information. And what we're doing first is called principal components analysis. And I will blur the distinction between the two, even though there's a difference, which we'll talk about maybe at the very end. But often people do principal components analysis, and they'll talk about it as factor analysis. In fact, in SPSS, if you do factor analysis, the default is what's actually a principal components analysis. The only distinction between the two is how it deals with that random error. Principal components analysis keeps all the information in, even the error. Factor analysis figures out what the error is and throws that out for you. Principal components analysis keeps everything in, which makes it more mathematically pure, which makes it easier. It makes a little more sense when you're learning it the first time, because there's weird stuff that may happen with factor analysis that doesn't happen here. So we're going to talk about, people will talk about calculating factors or principal components. You can interpret them the same way, and I'll, in fact, blur that distinction, I'm sure. So we've got these 4 variables, and can we repackage the information they contain into a small number of these factors, these principal components? Now notice, here's the correlation matrix. Yelling, how often does the parent yell, hug, monitor their child, and have rules, for behavior? And as you can, and this is all made up data, because I tried to make it really highly, made it work this way. So we see yelling and hugging are very highly negatively correlated, negative 0.95. So the more you yell, the less you hug. Very strong association. But yelling is really uncorrelated with monitoring and rules. Maybe a very small negative correlation. The more you yell, you may yell and still have lots of rules and keep an eye on the kid, or you may not yell and still have lots of rules and monitor what your child's doing. Hugging, same thing, highly negatively correlated with yelling, as we just said, uncorrelated with monitoring and having rules. So you can hug your kids a lot and let them go run free as a bird, or you can hug them a lot and keep your thumb on top of them all the time. So they're uncorrelated. Finally, monitoring and rules are highly correlated with each other. If you kind of have a lot of rules, you also are someone who's keeping a close eye on what your child's doing. If you keep a close eye on what they're doing, you tend to have a lot of rules. Again, this is all just made up data. For factor analysis, what you want to see in your correlation matrix are correlations greater than 0.3 at least, as a rule of thumb. If the correlations are all 0, what you end up with is there's no way to collapse the information. It's kind of like that what we saw with the hair color and IQ and weight, whatever. They're all uncorrelated. There's no way to repackage. They have nothing in common with each other. So there's no way to take information out of the hair color box and combine it with information in the height box, because they're completely unrelated information. They have nothing to do with each other. So you can't really repackage it in efficient ways.
So even though you have more information because you have different variables, it's not necessarily a good thing.
Not necessarily a good thing. It depends kind of, again, what you're trying to do. Sometimes you may have a lot of variables that are highly uncorrelated. What's your IQ? You may have a lot of things that you've measured very well, and you don't need to do factor analysis. And what that would tell you is, well, these, in that case, if the variables are uncorrelated with each other, hopefully that was intentional. Let's say I'm developing a parenting scale, and I've got 20 questions, and all those 20 questions are uncorrelated with each other. That's not a good thing, because it tells me they're all just random. They're all measuring things unrelated to each other. How can I say this is measuring parenting when I'm measuring things that are unrelated to each other? Unless, that should make you nervous. You want your variables to be, usually if you're making a scale, you want your variables to be correlated. Good question. But it is kind of funny, isn't it? So you want you want there to be overlapping information. Now, when you do, what happened? Oh, there we go. Oh, dang, is it going to do that again? See, I changed stuff to do this. Sorry, I'm talking to myself. Some of the information you see in a factor analysis, and that if you read an article where someone's talked about they've done a factor analysis, which, again, education, if you read any sort of quantitative studies, there's a good chance you'll come across this. They're going to talk about some of the information we see in this output. And the standard output you'll see in any sort of software that you're using. And the emphasis here is it's called initial statistics. And what it says is, okay, you're starting this process. Remember, factor analysis is kind of like building a tool. It's not hypothesis testing. We talked about that last week. I'm not using this to determine whether my intervention works or doesn't work. Or do kids in Vermont or Maine have higher SAT scores? Factor analysis is a construction job. You're making the tools, but then you'll use those tools for the research. This is just kind of behind the scenes. Let's build a better tool. Build a better workshop. Build a better workshop. Build a factor workshop. Oh, there we go. I need to remember that. Build a factor workshop. We could all build little. We could all build little factors. I'm going to think about this. So it's a tool. And so it kind of is helping us walk through the process. And it says, okay, here's your raw materials. We're going to build a factor. Here's the initial statistics describe the raw materials that you've got. Here, communalities is, we'll talk about this more in a minute, but notice they're all equal to 1. And that just means you're starting with all of the information in each variable. That 1 just means you've got 100% of the information in yelling, in hugging, in monitoring, in rules. It's completely meaningless at this point. It just means everything's there. And then the factors, it says, okay, before I do anything, the computer says, if you make 4 factors, you have 4 variables. If we reorganize those 4 variables into 4 factors, here's how much information is in each of them. Now, it's kind of interesting to think about, and this is what I like. This is why principal components analysis is useful for this. That think about, if I've got 4 boxes, so we're back to moving day again. I've got my 4 boxes of clothes, and I want to reorganize those. At a minimum, at the maximum, how many boxes will I need when I'm done? In the worst case, 4. I mean, I started with 4. I could shuffle stuff around. I could leave it exactly the same and end up with 4 boxes. I mean, you'd have to be an idiot to end up with 5 boxes. That's really, you're wasting. 4 is the maximum. You can fit everything. You can fit everything into 4 boxes because it's already been done. So with factor analysis, if we've got 4 variables, when we shuffle that information around, the most factors we're going to need is 4. Because we start with 4, we shuffle it around, we end up with at the most 4. Now remember too, that first box, what it says is, the computer determines how can I cram as much stuff as possible into that first box. And then the second box, then he comes to the second box and says, okay, among all this junk that's left over, how can I organize this to cram as much as possible into that second box? And then it gets to the third box. There's 4 variables. Now I'm down to the third box. How much is left over? How can I cram that into the third box? And then what's left over goes into the fourth box. The eigenvalues tell you how much cramming went on. Now eigenvalues, hard. People, this is that. Now we're getting we're into hardcore geek stuff. You start talking eigenvalues, it's pretty hardcore stuff for statistics. It's a measure of information in a matrix. So remember we started with correlation matrices. So it's how much information there is in our correlation matrix. And every variable adds 1. I mean, so it's kind of like that. Well, in fact, it's a lot like an R-squared for multiple. Remember, your R-squared is how much variance in that one dependent variable I'm accounting for. Now we've got 4 variables. The eigenvalues tell you how much variance in those 4 variables am I accounting for. So your maximum R-squared was 1, right? 100% of the variance for one variable. The eigenvalues The maximum eigenvalues 4 because every variable is contributing 100% of itself. So where r squared goes from 0 to 1, eigenvalues go from 0 to however many variables you've got. And where r squared tells you how much variance in a variable you're understanding, the eigenvalues tell you how much variance, how much variability, how much information in a correlation matrix are you accounting for. So we have 4 variables, and we see that first factor. That first box, when we've dumped out hugging, yelling, monitoring, all the information, and we've repackaged it, we're able to put 2.01 eigenvalues worth of information into that first box, into that first factor. How much of the information is that? Well, all you do is you divide 2.0163, whatever, divide it by 4, and you get 50.4%. So that first box has half of the information of those 4 variables. It's kind of cool. You're able to see exactly how much information is getting put into that box, into that factor. So we've already kind of reduced stuff down. Look, we started with 4. I'm down to 1, and I've already got over half the information. The second box now says, okay, that's kind of how the rules work. The first factor gets the biggest eigenvalue. It gets the most information. Then of what's left over, how do I repackage, how can I pack that in now to get the second most information, or the most information of what's left over? Our second factor has an eigenvalue of 1.94. Divide that by 4, we get 48.5%. So again, almost half the information is in the second box, that second factor. Cumulative here just tells us kind of as we're going along. With the 2 factors now, we've got 98.9% of the information with two factors. So this is that idea in a very simple way. We've taken all that information and we can actually cram it into 2 factors, 2 new variables, 2 new factors, and get 98.9% of the information. We're only going to lose 1.1% of the information, and we've cut our number of variables in half. Plus, it's going to reorganize it in ways that's maybe more understandable, may get rid of some of the issues with individual variability, individual quirkiness of, remember the dartboards, that no one variable is right on the money, but it's by combining it this way we're going to get a better estimate of what it is we're trying to measure than using 1 or 2 of the other variables. The third factor now, because there's hardly any information left, it just has an eigenvalue of 0.037, hardly anything, less than 1% of the information. And the final one has an eigenvalue of 0.00437, 1/10 of 1% of the variance. You add them all up for the 4 factors, it adds up to 100% because everything's there. We know we can repack 4 variables into 4 factors. So looking at this, we start to think, okay, looks pretty good that we could actually reduce the number of variables from 4 to 2. Now in reality, you'll do this and you'll probably have 20 variables or a dozen variables and maybe reduce them into 3 factors that only account for 60 or 70% of the variance, if you're lucky. I mean, that's more real world, but I've made this up to illustrate the point. Now it tells you, oops, I've just walked us through all of this. So I'm going to skip through all these. Oh, what a shame. Here, notice again, the first 2 factors accounted for 98.9% of the information of that variance. And it says at the bottom, PC, principal components, not the computer, extracted 2 factors. And what that says is it says all on its own the computer decided, because we didn't tell it otherwise. Kind of the default setting says take 2 of those factors and call me in the morning. I need some sleep. It picked 2, which makes a lot of sense, doesn't it? Because we saw 2 actually. 1, if you do 1, we're still losing half the information. 2 gives us almost everything. It's kind of like the 3 bears. One's too small, not enough. 3's too many. Look, that third one has hardly any information. Why waste it? 2's just right. So it on its own extracted 2. I should look at my.
It's like Goldilocks.
It's like, yeah, just right.
Still no question.
Yeah.
Looking at the 4 initial variables, what does this tell you about those 4?
That's where we're headed next.
So that's what I want to know.
This is just, it's kind of that initial information. It's saying, okay, let's before we figure out how to spin things around, let's get the lay of the land. Here's the variables. Here's how the information can be reshuffled. Then it's starting to get to work and it's saying, I'm going to extract 2 factors. Now, there's kind of as a rule of thumb, it's kind of interesting. Why? As a rule of thumb, the default from, I think just about any statistical software will say, if you don't tell it otherwise, how many factors should it extract? It'll always extract however many factors there are to have an eigenvalue greater than 1. Now, if you know why, that puts you probably a cut ahead of most researchers. We know, most researchers know the rule. Oh, I've extracted all factors with an eigenvalue greater than 1. We put that in our papers and send them off. And everyone, oh yeah, that's what you're supposed to do. But why? Most people don't really know why. Why is 1 so special? Why would we extract a factor if its eigenvalues 2 or 3, but we don't make a factor that has an eigenvalue of 0.3? And think about where does that number come from? What does 1 tell us? When we're coming up with that sum of the eigenvalues, what does each variable put into it? Into that total eigenvalues, which is, the eigenvalue sum to 4. 1 variable adds how much to that? 1. So if I've got a factor that has an eigenvalue of 2, you can think of it as that new factor essentially has 2 variables worth of information, 2 for the price of 1. It's more efficient. It's kind of, on the other hand, if the eigenvalue is 0.3, how much information is in it relative to variables? About 30% of a variable's worth. You're getting rid of variables to make a new variable, this new factor, that has less information than the average variable you started with. It's like you're digging yourself a hole. Why create a factor that has less information than what you started with? That's kind of the rule of thumb. Now, sometimes you'll make a factor that has an eigenvalue of like 0.8 or 0.9 because even though it's got less information on average than any single factor, any single variable, there's some really good information, a little bit, maybe 10% of you and 10% of you and 10% of you and 10% of you and 10% of you. And across all these variables, there's something there that's really valuable. And so even I'm still, when it adds up, the eigenvalue may not be huge. But looking at how the variables come together that we'll see in a minute, it says, wow, this is a very interesting piece of information that I've pulled just a little bit out of the other variables. So it's not a hardcore, hard, fast rule that you always say, oh, it has to be greater than 1 or else. But the default is always greater than 1. And usually, as a rule of thumb, that's what people do, and that's why they do it. So usually everyone just kind of knows that's what I'm supposed to do if they even pay attention to it. But that's where it's coming. It has less. The eigenvalue tells you how many variables worth of information is there. And if it's got less than one variable's worth, why would you go from this much information to that much information? Just stick with the original variables. So now we get in, so that's kind of that initial output. Then we get into the actual results. So as it starts doing that, it said, okay, I'm going to extract two factors. And that's just, the extract is just its way of saying, I'm going to reorganize this into two factors, into two boxes. I'm going to take all that information from the 4 and put them down into two boxes. It gives us a series of matrices. And again, all a matrix is, it's just a table of numbers that are in some way related, that gives us some information. The first matrix you see in factor analysis, or principal components analysis, is called the factor matrix. And what that does is it says, here's the two factors. Here's how we've organized. We've taken the information and reorganized it into these two boxes. And these numbers are called factor loadings. And all they are is the correlation. And again, a lot of people don't know this. All that is, that's the correlation between this variable and that factor. Just like when we had the streets and avenues, how close is that to that street? The closer the two homes were together, the more highly correlated. These numbers are just saying, how correlated am I to that factor? Am I really close to that factor? Am I really close conceptually that, look, my correlation is 0.92. It's almost measuring the same thing. And in spatially, now that weird statistical space, it's measuring, are you really close to that line going through that new road we made? What's that correlation with it? So these numbers are just the correlations between each of the variables and the factors. Now, we'll take a little bit of an aside, just to kind of, again, kind of make those parallels with what we've done before, and then we'll come back to this. But one of the things that's interesting, that remember in one of the nice things with principal components analysis, and what I like about it, what I mentioned earlier, it keeps all of the information. You can do this in a way that you throw out what looks like noise. And the argument is, I don't care about noise, so I analyze it. Principal components analysis keeps all the information in. So one of the neat things about it is, just like if we made if we reorganized our clothes into at least 4 boxes, we know we could keep everything. We could have kept that stupid hunting hat. We could have kept everything if you go from 4 boxes to 4 boxes. If we go from 4 variables to 4 factors, we can keep every piece of information. We don't lose anything. And what happens with that is, if you actually multiply the factor matrix by itself, you square the factor matrix, you will recreate the correlation matrix using matrix algebra. But to do that, you have to extract all 4 factors. And the idea, actually, if you're really interested, I could show you the slides where we go through those calculations. It's kind of cool. You exactly recreate it. On the other hand, we've only extracted 2 factors, so we lost information. We threw stuff out. It's worth knowing, what did you throw out? You know, you want to know, yeah, that really is a hideous hat. Let's get rid of it. So there's ways of starting to get a sense of that. Remember, we saw here, it told us what we're throwing out in our initial statistics. It said 2 factors gave us 98.9% of the variance. So the eigenvalues told us we're throwing out 1.1% of the information. So we're not throwing out that much. We know, again, now if we square the correlation matrix, if we square that factor loading matrix, it's not going to exactly give us the correlation matrix anymore. If we actually went through the process, here's what it is. We square it, we multiply it by itself. I hid those slides. What you end up with is, here's the correlation. You get this, what's called a reproduced correlation matrix. And if you do the output, this is kind of standard output it gives us. And a lot of people just gloss it over. They say, what the hell is that? Just show me the p-value. There's no p-value, which is really kind of funny when people come and say, show me the p, because again, it's not a hypothesis test. It's building a tool. So it's funny when someone asks, just where's the p-value? Anyway, this is very useful information. It's like the Rodney Dangerfield of the output, that it doesn't get its respect. That this bottom matrix, and it'll be one way or another. If you do SAS, you do SPSS, you do SysStat, it's there. But the informations are somewhere. Here in SPSS, it puts it in this lower diagonal of this reproduced correlation matrix. So that's not the whole correlation matrix, because remember, the correlation matrix is going to be parallel on the other side. This reproduced correlations just tell us, well, if we squared the factor matrix, here's what we would have seen for the correlations. It tells us what our results, it tells us how well the results recreate those associations. How well is it modeling the correlations in the real data? So we see here, like this says, our results, the two factors tell us the correlation between hugging and yelling is negative 0.97 if we just use the information in those two factors. Well, we saw earlier in the correlation matrix, the correlation is really negative 0.95. So again, it's not exactly right. It's pretty darn close. But it tells us that the two factors lost a little bit of information. And part of that information is related to the correlation between hugging and yelling. Now, you could go through and do all those differences by hand, but usually they'll also give you this in SPSS in these blue, highlighted blue. That's the difference between the observed and the reproduced correlations. You can think of it, it's just your error. How far off are you? So we see, we're off by, the difference is 0.017 for the correlation here, negative 0.037 for their correlation. It's a sort of thing, you look at it, and a lot of people say, like, so what? And that's why people gloss over it. But it's useful to know what happens. In this case, we see all of those correlations, the reproduced correlations. Our results, our two factors, do a very good job of estimating those correlations. We didn't lose too much. We didn't lose information. We lost a little information, but we didn't lose information about specific relationships. Sometimes you'll do this, and what you might end up finding is you lost all the information because somehow now it's saying yelling and rules have a really high correlation with each other. The information you lost is that these things aren't related to each other. And somehow, tossing out information, you might really screw up the relationship between a couple of variables. And maybe a couple of variables that's really important to you. You can kind of think of it this way. If the Chopin's not here, the information you lose, it may have a lot of information, but you lose the information in our relationship that we're married. The correlation matrix tells you, are you losing information about relationships between variables? And especially if I find that maybe yelling and hugging, it's saying, their correlation's only 0.4. In which case, so if it said like negative 0.4 here, then that error, that difference is going to be, like 0.5. That's going to tell you, wow, it's not doing a good job of describing how strongly correlated those two variables are. And it's an indication that there could be something wrong with your results with using two factors. They're not really describing all of those relationships. Maybe there's an important relationship they're missing. And so if you notice that some of these are really big, then you have to ask yourself, okay, well, is that relationship a big deal? If I'm losing that information, the yelling and hugging, people who yell tend not to hug. If I'm losing that information, what does that tell me about what this scale really is? Is that a problem? you may end up deciding, okay, well, maybe it's because one of these variables just really doesn't work. If it doesn't recreate the correlations, it tells you that maybe one of the variables isn't really measuring what you thought it did. That happens all the time. And you go back and you look and think, oh, great example of, did a study years ago asking kids, when I used to do a lot of research in juvenile delinquency, asking kids how often we had to measure, and we all reviewed it and signed off on it. One of all different questions: how often do you shoplift? How often do you steal? How often do you, all sorts of different behavior, and included how often do you go joyriding? Now, for me and my cohort in this was back at the end of grad school, and my advisor at the time, for us, joyriding meant that you would steal a car and go drive around. You wouldn't vandalize it. You'd just steal it, drive around, and leave it somewhere with the keys or with whatever. And that was it. We noticed as we were getting the results, though, we can pretend that this is how we found it, but this is how you might find it, that the results were crazy. We were finding honor students joyriding every weekend. And, it didn't make any sense. And so what it told us, there's something wrong with that specific variable that you may see here. So we went back and actually, next we were doing a bunch of assessments. Next class we went into and asked the kids, waited for some kids to start turning it in, and then kind of quickly glanced at some of their answers and pulled a few aside and said, what does joyriding mean? And all the kids uniformly told us, oh, that's when you go driving, or you take your parents, your parents let you use the car for the weekend, and you drive up and down the main strip in town, talking to your friends and getting burgers, and which we called cruising. So it was a meaningless. It was a good. The question just didn't fit. It didn't have the relationship that we'd expect to see with the other variables. This is how you detect something like that. So it's like, oh, drop. So what do? We drop that variable. It just didn't work.
So did you not have an operational definition?
We did not have an operational definition telling them what we mean by joyriding, which was, because the other stuff I think was pretty cool. We just, oops. Okay, let's. Then finally, this middle diagonal. Then we'll take a break. This middle diagonal has what's called the reproduced communalities, or in general, people will just call these communalities. We saw that at the very beginning when it said how much information is there for each variable, and it was 100% for every variable when you start. This says for each variable how much information is in those final two factors. So the correlations tell you how well do these factors capture every relationship. I like that. I got to remember to use this in the future. That the joyriding. Do I have a joyriding problem? We'll see in the correlations, because the correlations are going to be screwy, or maybe screwy. The communalities tell you. So the correlations say the relationships between the variables. The communalities tell you an individual variable, how much information for that variable is being kept, or am I losing a lot of? Do I lose when I lose that 1% of the information? Is it all in one variable? This is where you might see the problem of that 13th question about, oh, my friends are all behave well at school, or whatever it was. That's really unrelated to everything else. So that might be information that it just throws out, that it says this doesn't really pack with any of the other stuff. So the communality may be low. So if the communalities tend to be low, and by low as a rule of thumb, you'll see people talk like a 0.4. Again, this is all made-up data, which would be 40% of the information in the variable, at least. If the communality is like 0.2, it tells you there's only 20% of whatever information was there. You've only got 20% of it in these factors. So whatever that question is not being captured by these factors. That can also be very valuable. If you look and think, wow, this question is what I'm really, this is what I really want to know about. and it's not related to any of the other factors, that's a problem. Because if you really care about that, then those factors aren't measuring this. I might go into this thinking I'm measuring parental warmth or parental control or whatever, and if the question that I think, here's a great question, isn't sharing information with those factors, if its information's not captured in those factors aren't measuring this. And either I need to, one option would be add another factor. This is where you might add a factor even though the eigenvalue is a little less than 1, to put it in because you want to tap that information. You don't want to lose it. So add another factor and see if that new factor captures that information from that variable and maybe a little bit from the other ones. Or it's another sign, or it could be a sign that that one variable really sucks. It just is unrelated to everything else. I've done that too. Where it's like it's not measuring. It wasn't quite worded right. Kind of like question 4, 5, and 6 on assignment 5. It just didn't quite work right, so it's not giving me results. All these other ones are going together like I thought. This one doesn't seem to fit very well. So very little of its information is captured in those factors. Maybe add a factor if I think it is a good question, or drop the question because it's just there's something wrong with it. As part of that scale development, that construction of the measure, this is the whole meat and potatoes of it, that you start to get into. Okay, I'm starting with 20 questions, but you might end up with 16. Because you're recognizing, oh wow, this question, this didn't work, that didn't work, that didn't work. We did a big project, then I promise we'll take a break, a couple years ago, when I first started to hang out with the college, that helping to build an instrument for a large project that was going on. And it was an important project, and we wanted to make sure it was a good scale. So we started with 3,000 kids doing massive surveys at some schools. And we wanted to end with, I know I'm probably getting the numbers wrong, we wanted to end with about 50 questions. So we started with 3,000 kids and 150 questions. Factor analyzed it, threw out 100 of them that just didn't work right. That happens all the time. Added another 50. Did it again with another couple thousand kids. Threw out a bunch, added some more. Went through 3 iterations of adding variables, factor analyzing it, seeing what worked, what didn't work. And it's amazing sometimes afterwards when you look at it and you look at those results and you start to see, and it's like, why did I ever think those two are going to be related? It becomes, when you look at how they do relate to the factors, and it's like, I initially thought those two are going to be related, but no, they're complete. It's a fun, interesting process that it can be very illuminating. That wow, this really, there's two aspects to this part of parenting. We thought there was only one, but clearly, no. You can have good control and bad control. Or this question that I thought was so clear, that has the communalities stink, and then you look at it and you can think, that's not a good question. So it's a process, and again, it's a tool. So don't feel that you can't drop a variable, that you have to stick with the number of factors you started with. This is not a test. It's not a test of your hypothesis. You're building a tool, and that's how you want to use it. Okay, let's take a break, and then we'll look at some of the final. We'll look at the final statistics. Okay, so that's kind of the diagnostic, kind of that initial process of coming up with a solution. Again, we talked about how the default is to pick however many eigenvalues greater than 1. So you can go in and tell it, I want 2 or I want 3, or you can have it pick more or less than that, depending on, or set other criteria, depending on your own ideas. We then get to the final statistics. And again, it looks kind of very similar to what we saw before. But notice the communalities now are less than 1. And it's just giving us what we just saw in that diagonal. And that's, so how much information for each of these variables is captured by these 2 factors. So it's always good to look at the communalities and see how high they are. And you'll hear people, there's different rules of thumb that people will use. So that's why I hate rules of thumb. Certainly if it's less than 0.4, you have to think of it. You literally interpret that as 40% of the, if it's 0.4, it's 40% of the information in that variable is somewhere between those 2 factors. If it's 0.9, 90%, so that's really good. The eigenvalues tell you how much information is in each factor. The communalities tell you how much information of a variable is in those factors. So this is how much information from the variables is in the factor. This is how much information of the variables for each variable goes into the factor. Did I say that right? It's kind of the flip-flop, the complement of the other. Here's the factor matrix. We talked about that before. And you just interpret these as the correlations of each variable with that factor. And notice it doesn't give a label to it. It doesn't say it's, Frank or George or shoes or beach or whatever. That's up to you. I mean, the computer doesn't know what the variables mean. You have to come up with a label for what those factors are. So you just kind of ask, okay, so factor 1, if I've got a high score on factor 1, well, this is positively correlated. So that means I set a lot of rules, and I monitor a lot because the correlation is 0.89, so they're really highly correlated. So I must do a lot of monitoring. I do a little bit of hugging, and I don't yell very much. Versus if I'm high on factor 2, I do a little bit of rules, a little bit of monitoring. I never hug, and I yell a lot. The problems with that is it's doesn't really, that's not very good factors. I mean, they're kind of both doing, there's a lot of mishmash between them, a lot of overlap. It's not, the fact that, these are really high is nice, but these are pretty high correlations as well. So it's kind of like everything's related to factor 1 and everything's kind of related to factor 2. So how does it, trying to describe that, what does that mean? What does factor 1 or factor 2 mean? It can be very difficult. And you have to think about how it approaches to begin with. And this is where we said, well, we were kind of skipping a step with the packing and then talking about that rotation. The kind of that missing piece with the packing analogy, and we've touched on it already, I'm going to touch on it more bluntly now, is when it's repackaging that information. Notice we talked about, well, I'll put all the shoes in this, or I'll put the summer clothes in that box. That's not really how it works. All it does is the computer doesn't know, the math doesn't know that's a shoe or that's a hat or whatever. It just takes that information and figures out how it can get the most information along one factor. If you think of those roads, it just kind of is looking, it's building things blindly because it doesn't have any intuition to know what to call things or what's going to look and make sense. It just packs it to make the most information in the first factor, the second most information in the second factor, and rarely will this make sense just looking at it. This is this sort of solution you see all the time. This is where rotation comes into play. Because you can think about it as those original avenues and streets which made complete sense from a blind architecture, whatever, urban design sort of way. You can think of that as that initial factor solution. It said, okay, here's our streets, here's our avenues, here's our streets, and there's the relationships between the variables that are there. It just imposes something. It imposes that structure. These factors are that structure just kind of imposed on the variables in a way that streets and avenues capture that information of where everybody lives. But, and well, you can actually kind of see it this way. Actually, instead of for this initial solution, here's this dot is kind of the house, and you can think of factor 1 and factor 2 as the streets and avenues where you are, kind of where you're located. How close you are, how far along this factor, how far along that avenue is, you could actually measure that distance. And the distance would be 0.91927. That's how correlated. How far down you are is how correlated that variable is with this factor. And how far up it is, that number is how correlated that variable is with that factor. Actually, I kind of jumped. I said I got ahead of myself there. Let's look at rules. Let's look at the first variable. Rules has a correlation. Its factor loading is 0.91 and 0.38. 0.91 on factor 1, 0.389 on factor 2. That's just the correlation between them. But you can also think, again, it's kind of from that grid, where does it fit into this grid along factor 1 and along factor 2? So just like plotting any scatter plot, you just kind of move across 0.91 and point up 0.389, put the dot, that's variable. That's the rules variable. And those, how far up they are is just related to their correlation. Now, kind of at the same time, remember, this is going to be important in a second. Oh, I meant to add a slide. Shoot. Okay, I'll just have to remember where I was doing that. Let's skip. The communality, let's actually go back. If we take those correlations, if you take the correlation, square it, it tells you how much variance, right? The correlation squared is how much variance is related to that variable. If we squared that number, that 0.91 tells us how much of the variance in rules is related to factor 1. And if we squared that 0.389, that number will tell us how much of the variance in rules is related to factor 2. The factors are themselves uncorrelated. This is why we design the factors to be uncorrelated with each other. It's a term you may read called orthogonal. It's just, orthogonal means uncorrelated. It's just a geek way of saying they're uncorrelated. It actually comes from the geometry that spatially they're at 90-degree angles with each other, which is kind of cool. But because the factors are uncorrelated, and this is where I wanted the Venn diagram to show, here's the variance in rules. How much is related to factor 1? How much of the variance is related to factor 2? They don't overlap at all. Factor 1 and factor 2 are uncorrelated, so their R squared, that variance in the Venn diagram, doesn't overlap at all. So you can add those up, and you get 0.91 squared plus 0.389 squared equals 0.99685. And that's the total, that's the variance in rules that's related to factor 1 or factor 2. But that's what the communality is. How much of the variance in rules is related to the two factors. And sure enough, that is the communality. So it's all kind of related to each other in a wild sort of way. So those two factors, we square those factor loadings. We square those correlations between the variable and the factor. We get the communality. Now, if we plot like we just started to see, we could actually plot this just like our streets in Miami. Though there's not as many. This is the computer output. It doesn't show all the crossroads. But you can see this is factor 1. this is factor 2. Here's that 0, 0 to the middle of the city. And so we see, well, over here is, I go up 0.9, up 0.3, and I get, was it rules or rules? Up 0.38. And then we see monitoring is very close to rules because the two of them were highly correlated, just like when we did our map of Miami. And then hugging and yelling, we know are highly negatively correlated. So if you're high on yelling, you're low on, they're going in opposite directions. If you're high up here, you do a lot of yelling but no hugging. And if you're down here, you're doing a lot of hugging and no yelling. But it's kind of like we saw with Miami. They're not really lined up. It would be nice if, and this is where the interpretation becomes hard. Because what is factor 1? Factor 1 means you're going from yelling up to maybe a little hugging and then doing lots of monitoring. I'm not sure what to make. In factor 2, you're going from doing a lot of yelling to maybe some monitoring down to hugging. Again, not very interpretable. Can we, just like we did in Miami when we built the boulevards and lanes, maybe we can spin those factors around to line them up with the variables better, line them up with the natural nature of the data. Just like in Miami, we built the roads one way, but the houses ended up going some other directions. There was a natural pattern to the houses that the roads just didn't capture. So if we could spin the roads, we could line them up in a way that makes a lot more sense. That's where we do the factor rotation. The beauty is this, it does it for you. It'll actually do the calculations. You don't have to do the math. You may see this thing called a factor transformation matrix. This is the only time you'll see sines and cosines. These are just the sines and cosines for spinning those factors around in some multidimensional space. You just don't worry about that. That's just kind of, you take the unrotated solution, we spin them. It's like spinning the Price is Right, that wheel. I can do something with that. Or the Wheel of Fortune. You spin them around. It figures out what it does is, well, we'll see what it does. How you may wonder, where do those numbers come from? You multiply the unrotated solution, that initial factors matrix, by the transformation matrix, and you get what's called the rotated factor matrix. This is how it ends up. Now, the beauty of it is there's several different algorithms are out there that do this, that generally try to do the same function. What you try to do is maximize the big numbers and minimize the small numbers. So it just says, okay, how do I spin those factors around so that the numbers that are, the correlations that are close to 1 get even closer to 1, and the correlations that are close to 0 get even closer to 0. So can I spin the factors in a way that I end up with a lot of high numbers and a lot of low numbers? And now look, once we've done that, instead of talking streets and avenues, we talk boulevards and lanes. Now instead of talking factor 1 and factor 2, we're going to talk rotated factor 1 and rotated factor 2. And once you do the rotation, this makes a lot more sense. Look at this. Factor 1 is extremely highly correlated with rules and monitoring. If you're high on factor 1, you do a lot of rules, a lot of monitoring. And it's almost uncorrelated with hugging and yelling. So we don't even have to worry about this. You're high on factor 1, you're doing rules and monitoring, and you could be doing anything for hugging and yelling because they're uncorrelated. So it's easy to describe factor 1 now. Factor 2, really highly correlated with hugging and yelling. And the fact that this is negative is fine. You just have to make sure you interpret it reverse. So if you're high on factor 2, you do a lot of hugging and you do a lot of anti-yelling, non-yelling. You're never yelling. And it's almost uncorrelated with rules of monitoring. So again, hugging and yelling doesn't really tell us anything about those. So we can talk about factor 1 as a supervision sort of factor, and factor 2 is our warmth factor. You know, if you're high on factor 2, you're a warm, loving parent. Now, what's kind of interesting with this, notice all those loadings changed, right? The correlations changed, right? Because this went up, it went up a little bit, those went down a lot. But the communality doesn't change. If we go back to rules, and I square 0.99762, and I add that to the square of 0.04011, I still get 0.9685. I get exactly the same communality. Factor 1 and factor 2 account for the amount of information and rules that's captured by those two factors is exactly the same. Because remember, we didn't change when we spun the map around. We didn't change anything. We didn't change the relationships between the variables or anything. We just shifted the roads. So we're not changing anything other than we're just switching the scaling around a bit. So they count for just the communalities is still exactly the same, even as we've shifted stuff around. And visually, you can kind of see it here. Let's see if this will work. Here's our unrotated solution. And you can think all we're doing, just like when we saw spinning the streets, right? It's just rotating that around. So here, the rotated solution, now it's really close to factor 1. And it's almost completely related to factor 2. That's how that looks. Here's all 4 variables before we rotated it. And we saw it's kind of hard to make sense of what factor 1 is or what factor 2, because it's kind of not yelling and doing some hugging or yelling and doing some rules. When we rotate it, it looks like this. And notice one of the interesting things is it's not just rotating it clockwise or counterclockwise. It actually rotates it and completely spins it around at the same time, which is fine. It just comes up with, it'll spin it around whichever way will give it the solution most like something like this, to line up the factors with the actual variables, keeping those relationships, keeping all the information there. Because we saw the communality didn't change. So it didn't lose, rotation doesn't lose any information. We lost the information when we made the factors. Rotation's just shuffling the information around. And now we see hugging's really close to factor 2, yelling's really close to factor 2. They're both not even close to factor 1. Rules and monitoring are right on factor 1. So very clean result. Now, this is where it does get a little interesting, and think about it. We've shifted stuff around. The communalities stayed the same. Each variable has just as much information as before. But we've rotated stuff around. What does that rotation do to the eigenvalues? Well, think about the eigenvalues. If we squared, the eigenvalue is how much variance, what's the total variance of all those variables that's related to that factor? So we could actually just square each of those factor loadings, and that will give us the eigenvalue. Because, right, it's I square this number, it's how much variance in rules is related to factor 1, plus how much monitoring variance, square that, is related to factor 1. Square this would tell me how much variance in hugging is related to factor 1. Square that's how much yelling is related to factor 1. So if I squared all those and added them up, it would be the total variance in all of those variables related to factor 1, which is the eigenvalue. So let's do that and see what happens. Our non-rotated solution, here's before we rotated it, if we squared each of those, we got the eigenvalue of 2.0163, which was the right number. I've gone multiple more places for a point. And for factor 2, if I squared all of those, I get 1.9415 something something, which was the eigenvalue. If you go back in your slides, you'll see that was the eigenvalue for factor 2. So that idea does work. Squaring them is another way of getting the eigenvalues. And also helps to clarify exactly what the eigenvalue is. Here's the rotated solution. So I square them, add them up. Eigenvalue 1, the eigenvalue for factor 1 was 2.01. It's dropped. Now it's 2.00. It went down a bit. What about factor 2? I square 04, square 02, square 0.98, square negative 0.98, add them all up, I get 1.95. This went up a little bit. The sum of the eigenvalues is 3.95. Did I make that a point last time? The sum of the eigenvalues is exactly what it was for the non-rotated solution. So the total eigenvalues is exactly the same. But factor 1 went down a little bit. The eigenvalue for 1 went down a little bit, and the eigenvalue for 2 went up a little bit. Conceptually, going back now to our boxes, a way of thinking about that. Remember when the computer does the first packing for you. The computer comes along and says, let's cram, when we dumped everything out onto the floor. And the computer comes along and shoves stuff into that first box and shoves stuff into the second box, in this case. And the other stuff that's left over, you've thrown away now. And you come along now, and that's the unrotated solution. And you come along and you look at it, and it's like, okay, you've got the most stuff in box 1 possible, but I can't think of a label to put on it. There's no label that makes sense because it's just crammed stuff in. And same with box 2. It's got the second most information. What rotation does is basically takes a little of the information out of box 1 and puts it into box 2, and maybe a little of the information back, a little less of the information. It shuffles stuff between those two boxes a little bit. So that now you look at it, after you move a couple things around, now it's like, that makes sense. I needed to put the swimwear over here. Now it all works. I can put a clear label on what this box is and what that box is. That's what the rotation does. It's that extra little step to make the boxes interpretable for us. It doesn't lose any information. We didn't lose any information for the individual variables. Right? The communalities stayed the same once we did our 2 factors. We lose a little bit of information from one factor because we give that information to the other factor. So we don't lose any net information, but to help with the interpretation, factor 1 sacrifices a little bit of its eigenvalue to factor 2. And if you've got 3 or 4 factors, it'll shuffle it around. But the total eigenvalues will still be the same. They're just passing it around themselves to make a result that's more interpretable. So based on that, that's what's happened. That's the importance of rotation. Why you have to rotate, because rotating will help you come up with interpretable factors. I think, as I'd said, I was brought in for a student that was having trouble with their dissertation one time, and the problem is they forgot to rotate. They did the factor analysis, and then they had those really kind of weird factors that were hard to interpret and didn't make sense. And they did some analyses using that, which didn't make sense because it's hard to put a label on the factor. So I was asked to come and take a look, and we sat down and kind of went through the process and realized, oh no, they forgot to do this rotation. And once we redid the analysis and they rotated it, all of a sudden the factors came exactly what they'd hoped to see the first time, which was great, other than they have to redo then all the other analyses. But So make sure you always rotate. It doesn't, because you're trying to come up with a tool. And so shifting a little bit of information from one factor to another factor is fine. Because again, we're trying to come up with an interpretable tool. Now, once you get these two factors, there's a couple of things people will do. You can calculate what's called factor-based scales, and that's usually what people will do. Is they'll say, okay, these two variables go together, and so I'm going to maybe take the average of rules plus monitoring. I'll take the average of those two variables and create a new scale, or I'll add them up and create a new monitoring scale. And I'll do the same here. I'll add up hugging and yelling and create a warmth scale, keeping in mind that there's a negative loading for yelling, so I need to reverse that. You don't just add them up. If they're both 1 to 5 scales, you need to flip the negative ones around, right? So you just kind of rescore yelling, and then add them up, and you get this warmth scale. Those are called factor-based scales, and you'll see that done a lot. Nice thing with factor-based scales, they tend to be robust. If you do a factor analysis with one sample and I do another factor analysis with another sample, our factors are usually pretty close together. The loadings may be different, but the factors have if we've done the studies well, should be robust. Another alternative is to calculate what are called factor scores. Now, sometimes people will say they'll report things as a factor score, but what they really did are factor-based scales. The factor score, instead, is actually literally what that person's value would be along that factor 1 dimension. It's that unmeasured, let's say whatever that factor 1 is, it's kind of where would you be? We know where the variables are. We could actually go through and plot every individual person along those two dimensions. And so it's like, where are you in each of those factors? And you can do that. The computers will give you what's called a factor score coefficient matrix, and you just multiply you take every individual score, multiply them by these weights, and that gives you their factor score, kind of what your boulevard would be, what your lane would be, versus what we saw for the variables as well. More work. Until not that many years ago, software didn't even calculate this. I actually got a publication. I wrote software to do these years ago. Got a publication, and the letter from I won't say that on camera. You don't see factor scores. Where you see factor scores show up, the challenge using factor scores is it's more computationally messy. It's, summing up two scores, taking the average is pretty simple, pretty straightforward, very clean. The factor scores tend to change more sample to sample. Even if we both do a study with different samples, we'll probably get yelling and hugging on one factor and monitoring and rules on one factor in both samples. But these weights could be somewhat different. So it doesn't translate as easy from study to study. So in practice, you see factor scores done less. It's kind of built into structural equation modeling that it does this. But that's another lesson.